Okay, hello everyone. My name is Brian Carlson, my pronouns are they and them, and I am giving a talk today on SHA 256 interoperability, what's next. So hopefully this will cover a little bit of the interoperability work that's going on upstream. So let's talk a little bit about the background behind why we even want to do this and what we're doing in the first place. So Git currently defaults to creating repositories with SHA-1, which is the original hash algorithm when Git was created in 2005. Problem is, SHA-1 is weak and vulnerable to collisions. So in 2020, there was the Shattered attack, which basically made it possible to create collisions for SHA-1. And so around that time, in Git 2.29, we started supporting SHA-256 as an option, which is more secure and will be the default for Git 3.0. And the problem is we want a way to convert between these two forms, these two repositories, because there isn't a way at this point, and we don't want everybody to have to convert over all at once. For instance, if you have a server that has a SHA-1 repository or an existing repository, maybe an open source project, you don't want to have to force all of your users to switch over immediately. You want them to be able to take their time and update when they're ready. And so it's important that we have the ability to convert incrementally. So what is interoperability? So it's basically that our repositories can have a main algorithm, which is usually going to be SHA-256, and optionally compatibility algorithm, which will usually be SHA-1. And we can, with some limitations, fetch and push using either the main or the compatibility algorithms. This lets us convert a repository losslessly between the two algorithms. For example, if we have an older SHA-1 server, and we have a client whose main algorithm is SHA-256, with SHA-1 as the compatibility algorithm, we can then fetch and clone from that repository and push data to that repository, to that server. We can also then push that data to a SHA-256 server or interact with it in SHA-256 ways so that we can convert it and push it to a new repository, or in some cases, convert it in place. So the way that it works is our goal is to produce a lossless conversion as if we started in that algorithm to begin with. So the SHA-1 history is going to look like we've started exactly with an entirely wholly SHA-1 repository from the very beginning. All the commits, all the commit IDs, all the object IDs are going to be entirely in SHA-1. Similarly, the SHA-256 history is going to look exactly like we started very early on at the very beginning with SHA-256. So it's going to have all of the object IDs that are the longer 64 characters. But the conversion will have the same commit messages. It will have the same authors and committers. The only thing that differs will be the object IDs in the history. And there's the one exception here is that we will be able to sign a commit or a tag in one algorithm or the other or both and persist those signatures independently. So if we have older commits that are signed with SHA-1, and then we have newer commits, we can sign them with both or with SHA-256 if we'd like. And the conversion basically depends on the object type. The simplest form is blobs, because blobs are simply just data with Git uses prefix to determine their size and type and length. And we simply just hash them with both algorithms. So we don't have to do anything special to convert them from one format to the other, it just hash them. Every other type of object just recursively converts all of the object references. So I'll give you an example. So we have this tree here. This is a tree from the project this talk is in. And so in this case, we have two files. The first one is SHA-1, and the second one is SHA-256. And we're basically the only thing we're doing here for this tree to convert it is just replacing all of the object IDs for the blob. So we replace the blob object IDs, and then we hash it, and we get the new object ID for the tree. It's pretty simple. If we have more complex trees with other trees in them, then we have to first convert those trees. The script directory here is the one you just saw, that directory with the bootstrap script. And so we've converted that tree, and now we have the same object IDs, and now we have the blobs that we've converted, and so now we can hash these to get the new tree. So it's very similar the blob-only trees, except that we have to do the trees, convert the blob trees first. Then for commits, we have the same thing. We have trees and the root tree and the parents, and sometimes we can have multiple parents. We have to convert the trees, but you'll notice the author information is the same. The timestamp is the same, the time zone is the same, the commit message is exactly the same. It looks exactly identical except for the trees and the parents. We may also have signatures here, which will look a little bit different. I didn't show them here, but they basically will look very similar. And tags also will work the same way. They have an object reference and an object type, and the object reference will be converted. So converting these is pretty simple. The thing you have to notice about commits is that we have to commit, is that the parents have to be converted before the commit. So basically, you have to go all the way back down to the root and convert all the trees and the parents before you can convert a particular commit. So let's talk about repository storage. So the way we store a repository that's in compatibility mode is we store them all the objects and data in the main algorithm. The reason we do this is because it's not efficient to store them twice, and they might get out of sync. And so it's easier to just store them all in one algorithm, and then we convert them to the compatibility algorithm on demand. Now you say, well, we have to convert all these trees and blobs and commits, and that would be expensive. But to make that easier, we store a mapping of object IDs between the two algorithms. That allows us to convert an individual object on demand. So when you saw the commit previously, we already have the mappings between those trees and their parents. So converting the commit is very easy to do and it's relatively efficient. This is helpful when we want to push data to other repositories because it's much more efficient. We currently store the mapping in a text format, but soon we're going to use a more efficient binary format that's written, but it's not yet upstream. So there are some limitations on the interoperability functionality. The problem is the client of the server can only map data that it has. And as I said, mapping a commit requires mapping every previous commit, tree, and blob. When we have partial and shallow clones, as well as submodules, that means we have incomplete data. Partial clones emit trees or blobs, shallow clones emit part of the history, and submodules, the objects are in a separate repository. And so we don't have a full repository when we clone in this way. And so those are going to require help from the other side, usually the server in this case, but if the client is pushing, then the client will have to furnish this information as well. There's also the risk of security problems from sending submodules, because the submodule objects are, as I said, in a different repository, so we don't know what the mapping is unless somebody tells us. It's possible that a malicious remote or a malicious client for the server could offer a different commit in one algorithm than in the other. So for example, if I have a repository with both algorithms and I am using SHA-256, I could update the SHA-256 version of the repository to include a security fix, but offer an older commit to users using SHA-1. That would expose them to security vulnerabilities that would be hard to detect because the history isn't present. So let's talk about where we are with our upstream code. We have some code for this already upstream. I wrote this about a couple years ago, and Eric Biederman graciously picked it up and sent some of it upstream. So we have support for loose object mappings in a text format. This is basically an unsorted file mapping one SHA-256 value to one SHA-1 value, and it has to be loaded into memory in order to be efficiently searched. But all new objects are added to the mapping. So when you do git add, when you work with a repository in any way, all of these objects are added to the repository and added to the mapping. So they're automatically mapped. We have some commands, rev parse and cat file, that can accept either hash and can print either hash. So you can provide a SHA-1 hash and map it to a SHA-256 hash or vice versa and work with that. And that's about it. This was only maybe 10, 20 patches, so it's not a huge amount of work that's upstream. Good news is we have a lot more that's written. Taylor suggested that I give a talk, and I graciously accepted this talk. So I thought I'd do some work and say, okay, well, what could we do to improve things? And I've actually written quite a bit since that point. So we have loose object mappings in a binary format. And it allows storing the shallows, submodules, and partial clone mappings as well. Because as I said, we need to get those from the server, and we need to store them locally, but we don't have a way to store them in a dedicated way, so we use the loose object mapping. We also have the ability to filter out we also have the ability to store certain types of data, like what kind of object it is. So when we update the shallows, we can remove the old values. We can prune old data that we don't need anymore. This also works better with push quarantines because our push quarantines don't gracefully handle two files with the same name. The binary files are stored by their contents, and the older text mapping was stored in a fixed file, which meant that Git could not merge the two data when you push, and that would result in problems with push quarantines. So this approach works better and is more robust for pushes, which we want. We do have packed object support. So part of the original design of the hash algorithm transition was pack index v3, which maps two different algorithms or more algorithms, if we want to do that, in the same pack index. So we don't even have to actually look at the objects. We can simply just look at the index to determine the mapping. We also have support for fetching and pushing for full clones of submodules. This already works. If you are cloning from a different repository, the index pack process will rewrite your repository, rewrite the pack into your native format, and it will automatically work. This format always keeps data in packs because it's simpler and more efficient that way. Pack index is more efficient than loose object mapping, so we use that for efficiency. We also have protocol extensions for mapping objects when pushing and fetching. So we need to provide these mappings when we do shallow clones or partial clones or submodules, and we have support right now. I finished it about 4:30 this morning for shallow clones and fetches with protocol v2. It works. You can unshallow a repository, you can clone a shallow repository, you can deepen a repository. It's pretty simple. So there's a lot more that we also need to write. We need to write lots of tests. For instance, we have some for pack index v3, but we want to add more to make sure it's robust and that people changing it in the future don't introduce regressions. So we need to add a lot of tests and a lot of more functionality, and we also need to fix a lot of existing tests that are broken in compatibility mode. Mostly because we're missing support for partial clones and submodules, but also other types of things in the future. We need to do lots of various cleanup. For instance, our delta resolution, when we're converting objects, uses recursion. That's not a good idea when you're dealing with untrusted data because the remote side could send you very deeply nested data that results in a Stack Overflow. So we're going to move in favor of iteration for those kinds of things. We need to do kind of cleanup and robustness testing and things like that to make it something good quality that users are going to want to use and not submit lots of bug reports to. We also need to add shallow clones and fetches for protocol v0, which should not be too difficult, but I just haven't gotten to it yet. Shallow pushes, pushing to a shallow repository, pushing from a shallow repository, if we want to add support for that. We want to add support for partial clones because those are very common for large file use cases, which we want to support, and submodules, because even the Git repository has submodules. We use SHA-1DC as a submodule, and we're going to want to convert the Git repository at some point so people can continue to use it. So we also need to write quite a bit of other stuff as well. We need to do some garbage collection and compaction for loose object mappings. Because as I said, as you unshallow a repository, you will have unneeded shallow points, and we don't want to waste space by storing mappings we don't need. Similarly, if we pull down objects and they're stored in a pack, we don't need those partial clone object mappings, so we don't need to store those anymore. This will also help preserve the efficiency of a repository because we'll get rid of unneeded data and we'll compact it into larger files, so we'll have to read fewer files. We also need to do batch writing for loose object mappings because currently we write one file per object. That's not very efficient. If you do git add, you want to write one loose object mapping for say 200 files and not 200 loose object mappings because again, that's not very efficient. So that's one of the things I'm going to be working on next. And we also want GitFS check to do the verification of mappings because it could be that something gets subtly corrupted or there's a bug, and this will help us detect that and find any problems before they spread. Especially because servers will also want to have this so that they can have a robustness against insecure clients. So the final things we want to do are get a conversion script for existing repositories. Because with submodules, you need to convert the submodules so that you can get the mappings between the commits in the main repository. And that's important. We want, obviously that works important for Git, but we also want to do a variety of other projects as well. This is also going to be generally helpful for users and forges as well, because you can do this with Git fast export and Git fast import, but it's kind of a pain in the butt and nobody wants to do it. And so having a script that just converts it for you easily is going to be really convenient. And it will be a part of our goal is to make it more user-friendly, and we want to make it as easy as possible. And then the final thing that we're considering adding is handling objects of either format in commands. The Git project originally thought this was going to be implemented as part of the hash function transition. It turns out that it's actually very complex, and there's a lot of work, so it's pretty extensive, and we may not make it into Git 3.0, or it may not ever be written. It isn't out of the question entirely, but it is a kind of a stretch goal of things we want. So that's basically what we need to write for this, and that's what's next. So thank you very much. That's it.